In 2006, Rolls-Royce staked its future on a single gamble, building the world's most advanced jet engine for Airbus's A350. No backups, no second chances. The official story celebrates the Trent XWB as a triumph of engineering, powering airlines across the globe. Yet buried beneath the praise are boardroom battles, perilous tests, and industry-shaking secrets that could alter the fate of commercial aviation forever. So why did Rolls-Royce risk everything, and what did it cost to win? Sir John Rose gathered his executive team in Derby as the Airbus A350 contract hovered between opportunity and disaster. The year was 2006. Airbus wanted a new engine, one that would outclass Boeing's best and power the next generation of long-haul travel. But there was a catch. Airbus demanded exclusivity. Rolls-Royce would become the sole supplier for the A350, with no safety net, no alternative engine partner. The boardroom air was tense. Engineers warned of technical leaps required. Higher thrust, lower fuel burn, and reliability targets no Trent engine had ever achieved. Finance chiefs presented risk models showing billions in capital on the line, and confidential memos circulated with dire warnings. Failure could threaten the company's independence, even its survival. The decision fell to Rose. He saw the stakes clearly. Either Rolls-Royce would double down, betting its future on a single all-or-nothing engine program, or risk slipping into irrelevance as GE and Boeing tightened their grip on wide-body aviation. In closed-door meetings, Rose's message was blunt. We win this, or the company changes forever. By signing the exclusive pact with Airbus, Rolls-Royce locked itself into a path with no exit. Every engineering resource, every pound of capital was committed to the Trent XWB. The gamble was existential. If the engine failed, if it missed performance, schedule, or reliability targets, Rolls-Royce would face not just financial loss, but the possible end of its leadership in civil aerospace. The commitment set in motion a cascade of technical and commercial pressure that would test the company's resolve at every level. The first challenge facing Rolls-Royce's engineering teams was not just to meet Airbus's demands, but to leapfrog every rival in the wide-body engine market. The Trent XWB's three-shaft architecture, a hallmark of the Trent family, allowed each spool, low, intermediate, and high pressure, to spin at its most efficient speed. This design gave the XWB a crucial edge in fuel burn and durability, especially when compared to two-shaft competitors like GE's GGENX and GE90. At the heart of the XWB sat a 3-meter carbon titanium fan, the largest and lightest Rolls-Royce had ever produced. The new composite construction shed weight while boosting strength, moving more air for less fuel. With a bypass ratio of 9.6 to 1, nearly 10 times as much air flowed around the core as through it, delivering quieter operation, cooler exhaust, and a step change in efficiency. The pressure ratio climbed to 50 to 1, setting a record for civil engines and squeezing maximum energy from every kilogram of fuel. Every major system was reimagined. The fan case was reinforced to handle higher loads, while the single crystal turbine blades, products of years of materials research, could survive temperatures above the melting point of their base metals, thanks to advanced cooling channels and specialized coatings. These technical leaps set the XWB apart not only from its Trent 900 and 1000 predecessors, but from GE's flagship engines as well. The GE90, with its even larger fan, delivered more raw thrust, but lagged behind in fuel efficiency per seat. The GENX, while advanced, could not match the XWB's bypass ratio or pressure capabilities. Engineering ambition reshaped every component, but it also brought new complexity. As the first hardware rolled off the line, the true test would be whether these radical ideas could survive the scrutiny of regulators and the demands of airline operations. August 2009, Derby. The containment test cell was set for a trial that every engine must survive. Simulated bird strike, full thrust, no margin for error. Onlookers crowded behind thick glass as the Trent XWB's massive fan spooled up. The test bird hit. Seconds later, a dull crack echoed through the cell. Instead of the expected controlled blade off, the fan containment ring warped under the force, scattering debris. Engineers watched in disbelief as sensors tripped and alarms sounded. Certification was now in jeopardy. Regulators demanded answers. The engine's entire future hung on a fix, and the clock was ticking. Within hours, a crisis team assembled in Derby. Senior engineers pored over high-speed footage and metallurgical data, searching for the flaw. The analysis pointed to an unexpected deformation in the composite fan case lining and a stress concentration at the blade root. With only 72 hours before the next slot for a repeat test, the team reworked the blade geometry and reinforced the fan case lining. Parts were machined overnight. By dawn, technicians installed the modified components, working through fatigue and mounting pressure. The revised engine passed the retest, but the setback forced a 3-month delay in the A350's engine type certification. Regulators intensified their scrutiny, and Rolls-Royce's leadership faced tough questions from Airbus. The episode became a defining moment for the Trent XWB program, a public demonstration of both vulnerability and resilience. For the engineers in Derby, the memory of those tense days would linger long after the crisis passed. By 2011, the Airbus A350-1000 was no longer just a paper airplane. Airlines wanted more range, more payload, and most of all, more power. Airbus negotiators pressed for an uprated engine, 97,000 pounds of thrust, a leap far beyond the original XWB-84 design. Inside closed conference rooms, the mood was tense. Rolls-Royce engineers warned that pushing the engine this hard would test the limits of their materials and thermal management systems. The XWB-97 would need thicker fan blades, a stronger fan case, a larger core, and a new high-temperature alloys. Each fix added millions to the development bill, and every change risked schedule delays. Airbus, facing its own pressure from customers eager to rival Boeing's 777-300ER, insisted on the uprate. The threat of looking elsewhere for an engine supplier hung in the air. Rolls-Royce's program managers, led by Chris Challerton, pushed back. The company could not shoulder all the costs and risks alone. Talks stalled, then restarted behind closed doors. Both sides knew that failure to agree would jeopardize the A350-1000's future and expose billions in sunk investment. Eventually, a compromise was hammered out. Airbus agreed to share a larger portion of the non-recurring engineering and certification costs, breaking with industry tradition. Rolls-Royce committed to delivering the uprated XWB-97, but warned that the new technical demands would require careful management of stress and reliability. The deal kept the program alive, but the strain showed. Engineers now faced a compressed timeline, heightened scrutiny, and a technical envelope stretched to its edge. The commercial gamble had moved from the boardroom to the test stand, and the outcome would depend on whether the XWB-97 could deliver both the power and the reliability the market demanded. Shows in the 12 million flight hours. That's the number Rolls-Royce cites when describing the Trent XWB's track record across the world's major airlines. Dispatch reliability sits at 99.9%. An industry high that means nearly every A350 flight leaves on time, with engine issues almost unheard of in daily operations. But behind these headline figures, airline engineering teams have tracked a different set of numbers. Maintenance costs for some operators have run about 13% above early projections, driven by unexpected wear in the engine's hottest sections, especially in regions with relentless heat and airborne sand. Engines operating in the Middle East and parts of Asia have needed more frequent inspections and earlier part replacements than those in cooler climates. For fleet managers, the promise of near-perfect reliability comes with a hidden price: higher shop visit rates, more downtime, and a constant push to refine thermal management. These pressures shape every decision about where and how the XWB is flown. September 2, 2024, Cathay Pacific Flight CX-383, powered by Trent XW. B-97 engines returned to Hong Kong after an engine fire broke out during climb. Investigators traced the cause to a ruptured steel-braided fuel hose connected to the number 17 spray nozzle, a component that had passed all standard checks before failure. Emergency inspections swept through the global A350-1000 fleet. Within days, the European Union Aviation Safety Agency issued a directive mandating urgent checks on 86 affected engines. Maintenance logs revealed similar defects in hoses from the same batch, all linked to a modified cleaning process at a third-party overhaul facility. For airlines, the costs ran into millions. Grounded aircraft, rerouted flights, and the specter of a deeper quality control problem. Rolls-Royce responded with a service bulletin and a recall, but the incident exposed the fragility of even the most advanced systems. As UltraFan development ramps up, promising a 25% leap in efficiency, the question lingers. Can lessons from the XWB's hard-won victories and failures truly carry forward, or will new ambitions open the door to risks yet unseen? With over 12 million flight hours and a 99.9% dispatch reliability, the Rolls-Royce Trent XWB stands as the most efficient large aero engine ever built. This achievement followed a high-stakes 2006 boardroom gamble, radical engineering leaps, and the urgent response to a 2009 containment test failure. Yet the September 2024 Cathay Pacific fire and ongoing maintenance overruns, 13% above projections, highlight the real-world complexities behind the statistics. Key details about time-on-wing challenges and long-term cost-sharing formulas between Rolls-Royce and Airbus remain undisclosed. What's certain is that every lesson from the XWB shapes Rolls-Royce's next generation, the UltraFan, targeting a 25% efficiency gain over first-generation Trents. The true legacy of the Trent XWB is still being written, on the ground, in the air, and in the engineering labs where the future of flight is decided by fact, not just ambition.